So in this section 4.2, we're looking at linear versus exponential word problems. And so we're going to look for the keywords that would indicate addition for linear or multiplication for the exponential. What's really important is writing down these formulas so that you can create the word problems. And so when I look at these phrases below, I'm going to select ones that have keywords for addition. So these would be examples of linear. So decreasing by 0.5, they're telling me a specific value. Double means times by 2. 10% of, well, I need to know what that percent is of. And so that is, again, multiplication, just like doubling. Subtracting is the same as adding a negative. Multiple of 4 means times by 4. Half of, so I need to know the beginning number. So that's multiplication. $7 each time, that's addition. Increasing by 5 is another addition keyword. Are there others on here? Yes. Adding and +3 would also be keywords for addition. On the next slide, we'll look at keywords for multiplication. So the exact same stuff here and the exact same stuff. So now I'm just selecting the ones that are multiplication. 10% of, that'd be 0.10, multiple of 4, yes. Doubling, and then half of. These are all the exponential keywords, at least on this list. So let's take a look at some examples. So we've got a library. And so the library starts with 7,000 books and is adding 500 more each year. So it clearly said the word adding, so I know for sure that it's a linear pattern. And so what I'm going to do is I'm going to copy paste this linear equation, Control C. Let's see if it worked, Control V. Perfect. And I'll select linear. And then I need to just fill in the starting value and the rate. The starting value is going to be 7,000. And the rate is 500. And now I have created an equation for linear. So sometimes that's going to just be that easy. The two numbers, it said adding 500 each time. So I have to submit and explain. So of course, 500 is the rate because it says adding. And the rate goes with the word per. So per year is usually how we know that it's a linear rate. So let's take a look at our next one. In this problem, we've got a bank account started with $8 million, and every year the amount doubles. Doubles is that key word for timesing by 2. So this one is going to be exponential. So I'll copy and paste the equation here, Control C, Control V. And again, I'm filling in the starting value and the rate. So the rate doubling means timesing by 2. So that means that the rate is going to be 2. And the starting value was 8 million. So 8, and then 1, 2, 3, 4, 5, 6. So I want to explain this. Doubling means to multiply by 2. So the rate is 2 for exponential. So hopefully it seems pretty simple and straightforward for these first two. You see the starting value and you see the rate pretty clearly. And we're able to use those equations with copy and paste, just filling in the blanks. So it's a lot of fun. So here, word problem number 3, we're at the carnival. You start with 50 tickets and each ride costs 6 tickets. So that's going to be linear. They tell me exactly how many each ticket is. So I've got y equals, the rate is 6 tickets, but we have to remember that that means take away 6. It costs us 6, and then we started with a positive 50 amount of tickets. So this is negative 6x plus 50. And then here we've got GameStop. Use Robinhood to invest your $50 in GameStop and your money quadrupled. Quadrupled is the keyword that means multiply by 4. So this one will be exponential because it's a multiplication pattern. So I'd say y equals, I started with $50 times quadruple, 4 to the x power. And so to get the times, I use the asterisk on the 8. So I hit shift and then the number 8. And then to get the exponent for the x, I do shift 6 because that has the little caret. And that's how I can use just the keyboard to type in the equation. On word problem number 5, we're looking at this beautiful bird, the endangered fruit dove. And it says the population was 4,000 and decreases by half every year. So the first year would be 2,000, then it'd be 1,000, and then 500, etc. So that's going to be, again, exponential. The starting value, so we've got y equal, the starting value is 4,000 times, so, and then half. So I just do the slash, and then I put my exponent of x on this fraction. And that's how this equation would work. Got a couple more just to look through quickly. We've got the population of bunnies doubles every 3 weeks. So unless I have a number of weeks, I'm just going to sort of ignore the 3 on this. I can tell that it's exponential because it's doubling. So I've got y equals a pair of bunnies means 2 bunnies. So we started with 2, and then we're timesing by 2 every 3 weeks. So we just use the weeks if we were trying to answer a question. So if it was 6 weeks, then we would do twice. And if it was more weeks, like a full year, then we'd need to figure out how many weeks that was. Word problem 7. JJ has $400 and earns $250 every week. So 250 is an exact number. It's not a relationship. So I know that it's linear. So it's y equals 250 per week is how I could say that. So 250 is the rate, plus started with $400. So these are a lot of fun. I just use the 2 numbers, put them in the right spot once I decide if it's linear or exponential. And then here's word problem number 8. Working for Ulta Beauty, Sam earns $18 per hour. And so I don't see anything about the starting value there, which is very interesting. I know that hourly pay is linear. It's y equals 18 per hour x. And then the starting value is not mentioned. And so in that case, I do assume that it was $0. So I could say plus 0, or I could just say 18x. And this is important because when you have a job, you are usually going to be paid an hourly salary, and you can create an easy linear equation just like that. Just a couple more. And so, now we're switching over to percentages, and this is the really fun part. And so when we use percentages with these exponential and linear equations, we've got 1 plus the percentage rate for growth or appreciation. That's a fancy word for growth. Or we have 1 minus the rate for depreciation. So remember, when we are moving percentages, we move the decimal 2 places to the left. And so we change it to a decimal first, then we add that decimal to 1. So we're seeing the example here with 15%. So we change it to the decimal, then we add it to 1, and it looks like just the number 1.15. And so here I've got 1.05. That would be an example of 5% growth. 1.1, so that's 1.10, that'd be an example of 10% growth. 1.5, that would be an example of 50% growth. 90x, that's linear, and 0.5, that is 50% decay. And so that's very interesting. We want to select those top 3 or those ones that are larger than 1 because they're exponential growth. And so looking at this first equation to make sure that I understand it, I've got the 0.25, 1.25, so 0.25 is 25% growth. So 25% of 800, that's the growth. And then the second one, the decay, it's 0.9. So what I really have to think there is 1, hey, it was 1 minus this unknown percent is equal to 0.9. So I know that it's 1 minus 0.10 is equal to 0.9. And so this is 10% decay. Of 800 again. So Frank, I'm just going through these notes one more time for students who are absent. I'm going pretty quickly though. So I want to explain that 0.25 is 25% and easy to see, but the 10% from 1 makes the 0.9 or 90%. So this is the pattern. We've got this formula, y equals p 1 plus r to the t power, because these are usually used in banking formulas. P stands for principal, and it's the starting amount. R is the percentage rate as a decimal, and T is usually the time in years. So if I want to use that formula, I can again copy and paste it. Control C, Control V. And then I'm going to replace the starting value with the numbers. So an equation that has the starting amount of 100, so starting amount is 100. A growth rate of 7%. So 7%, remember we move the decimal place over 2 times. So I've got the 7. Okay, that's not working. So I'll just type it in. That'll be 0.07. And then the T, I'm going to change that to 8. And so what's cool is Desmos does the calculations for me. I love that. And then a nice way to write it is I get rid of that plus and I just combine it to 100 times 1.07, which is really cool. So I love these because these are very advanced and we actually use these formulas in real life a lot. So here I've got a decay. So if I'm doing this equation, I start with copying. So with decay, the rate is always less than 1. So that makes it get smaller. So I started with 100 again, $100, and decay rate of 70%. So 70% is just 0.7, and then the time is 2 years. And now I'm left with just 9. So remember 1 minus 0.7, that's like 100 and you lost 70%. So that's the same as 0.3. So wow. So 100% minus 70% leaves 30%. And that is how I get the decimal of 0.3 for the rate. So we're going to look at a couple more examples with these, and that'll be it. So if I've got the formula here with what I'm trying to show is a plus or minus. We use the same formula, sometimes plus, sometimes minus. So the investment started with $300 and increases. Okay, so that would be plus by 4%. So we got 300 times, and then I am already trying to figure out, okay, 4%. So I've got the 1 plus 0 point, it's 0.04. So that makes 1.0. So 1.04 to the 19. So 19 years to the 19th power. And now I get my answer. It's cool because Desmos tells me that it will be more than doubled. It will be $632. All right, cool. Let's try another one, just trying to set them up. Write an equation for the word problem. A home originally purchased in 2005 for $250,000 has appreciated 11%. So I know that I start with 250 and 11% is 0.11. So adding that to 1, I get 1.11. And then from 2005 to now is 16 years. So when I go to type this in, I've got y equals 250,000 times 1.11 to the 16th power. So now they're showing me the scientific notation. And just to kind of refresh your memory in case you are a little rusty on this means that I take the 1.3277 and this 10 to the 6th means I move the decimal place over 1, 2, 3, 4, 5, 6 times. So I'm going to fill in those missing spots with zeros, telling me that the answer is actually $1,327,700. Pretty big amount of money. And it has the approximation symbols, meaning they've rounded that answer. So that's pretty cool about that scientific notation. You get to move the decimal place over 6 times for that exponent of 6. 3 more. So here, this Honda CRV originally valued at $34,000. So I know, okay, the original amount was $34,000. And then it says depreciates. So that's going to be decay. Depreciate, decay. So I'm thinking 100%. It's easier for me to think of 100% minus 18%, right? So that's going to be 82%. So when I change that, it's going to be 0.82 when I do all of this work. That's what I was doing there. The 1 plus the percent, 1 minus the percent. In this case, I'm doing 1 minus the percent. So times 0.82, and then for 5 years, so to the 5th power. And so it's 12,605, which makes sense. It should be smaller than the original amount. And that's true. When you buy a used car, it's cheaper than buying a new car. And so that's kind of that formula for that. And I think they actually go with 17% is the average depreciation rate, not 18%, but whatever. So word problem number 12, the landfill of 60,000 kilograms decays at a rate of 25% per year for 40 years. So I start with 60,000. I times it by, so decays, so I'm doing subtraction. So 100% minus 25% is 0.75. And that's going to be to the 40th power. Costs, I can't see the clock right now, 9:03. Yes, I believe it is over. But if you need, I want to finish this one last example for students that were absent. And so here's word problem number 13, the last one. A Porsche 911 bought in 1993 for $35,000, appreciated, which means goes up in value. So that would be 5,000 times, okay, so it goes up 3.5%. So that's like you got 103.5% on your quiz, so 1.035. And then since 1993, 20, my pen is not working. 2021 minus 1993, that's the math I'm going to do in my calculator to figure out how many years it's been. Oh, that's too hard. I'll say it was 7 years to 2000. And then to 21, it was 21 years, so that'd be 28 years. To the 28th power. So now it's worth 91,000. And that's that. So the last slide is just for you to summarize. And I think it was fun. Maybe you don't.
However,